The first example we're going to look at today asks you to design a digital circuit that would implement this equation. So I look at this equation. It's a little bit long, but it's feasible. It's one thing that I noticed that it's very good in the first place is that it is definitely in the sum of products form. So I'm going to write SOP out here to the side to confirm to myself that it is in fact in the form of three products. So I have not A and not B and not C. Then I have not A and not B and C. I have not A and B and not C. So I have three different products. Those are going to yield three different AND gates. And then I'm going to OR those three AND gates together. So I'm going to go ahead and draw the first portion of this. I always do the right hand side of the circuit first because it's actually quite a bit easier than the left hand side. So this is where all the gates are, but it's also the easiest part of the circuit. And so I like partial credit, and therefore at this point that I have now drawn three AND gates, each of which has three inputs. And the outputs of those AND gates are going into an OR gate, and I have F labeled over here. I've probably honestly earned myself at least half credit, and it took me, 20 or 30 seconds to be able to do that. Now, all of the actual work comes on the left-hand side over here. I'm going to have three variables. I can see that in this first AND gate, it'll be this AND gate right here is going to be this term right here, and then this one will be this one, and then this AND gate will be this product right here. So for the first AND gate, I can see that all three of the variables are going to be inverted, so I might as well just go ahead and toss three inverters in here. And I'm going to go ahead and send those in. And this will be A, and this will be B, and this will be C. Okay, it's about to get a little bit messy here. I need not A, not B, C. Okay, well, I'm going to need not A, so I'm going to take it off of here, draw the dot to indicate that you made a connection, draw the little curvy thing to indicate that you did not make a connection. So it's a little hopper. Okay, so there is that one. And I also need not B. So I'm going to grab not B here, skip over there, come over like this, and then I need C. So that's going to come over here. It's going to go in like that. The third term needs not A and B and not C. Okay, not A. The closest place that not A is available is right here. So I'm going to grab not A, skip, come down to here. And then I need B. Well, B is available way over here before you invert it. And then not C. Whew, I wish I would have left myself a little bit more space, but there is the connection that I can make to not C. And there is a completely miserable solution to this problem. But if you were only asked to design a digital circuit that will implement this equation, that is a solution. It's one that I'm not proud of, though. So let's move on. Please use Boolean algebra to minimize the complexity of the equation and redraw the circuit. Okay, that'll make my life a lot better. I'm going to zoom out a little bit so we can keep the equation on the screen here. I'm going to look at that equation. I see that the first two terms, the first two product terms, have a not A and a not B in them. So I'm going to rewrite this as F equals not A. It's going to be not A and not B, and if there's a C bar from term number 1 and there's a C from term number 2. Now then we have to, don't forget the third term, not A and B and not C. Okay, we can now say this is going to be equal to 1, and we understand that if you AND anything with 1, you get that thing back. So now I have F equals not A and not B, or not A and B and not C. Okay, I'm going to factor a not A out of both of those terms. So I have not A and not B, or B and not C. So we've encountered equations of this form before, and what I'm going to say is this is what we have previously referred to as X. This is what we have previously referred to as X bar. So this one is X bar. And that means that this is Y. Because remember, we saw that X or not X and Y is just equal to X or Y. So what this is going to be equal to is not A and X is B bar, and Y is C bar. So that step is a little bit hard there, but what I would recommend is try to identify the thing that is x, the thing that is x bar, and the thing that is y. Now I'm going to go ahead and distribute the a bar and give me one last form of this equation. I have not a and not b, or not a and not c. So I can implement either of two forms. I can implement this one, or I can implement this one. Now, the good thing about solution number 1 is that it is probably going to be the simpler solution. The good thing about solution number 2 is that it is in sum of products form. For now, it says minimize the complexity. That means to make it as simple as it can be. So I'm going to take expression number 1. So I need to have I'm going to have an OR gate first. The inputs to the OR gate are going to be B bar. So there is B bar, and then there is C bar. So I've ORed together B bar or C bar, and then that needs to be ANDed. That needs to be ANDed with A bar. So this is a solution to a circuit that will implement that digital logic as well. One thing that you might notice if you are really, really paying attention is that we could use De Morgan's theorem to replace this with B NAND C. And if we did that, we would eliminate the need for 2 of the inverters. We might even be able to get away with De Morgan's theorem a second time and reduce things down even further. But to be honest, at this point in your curriculum, this is the solution that I was looking for. Of course, if you're going to go ahead and go a step further and get De Morgan's theorem to make it even simpler, God bless you. I think that'll be even better.